Hello and welcome to our next lecture. Today we're talking about method of partial fractions and how we can find inverse Laplace transforms using partial fraction decomposition. We have already invoked this method in the previous lecture, so today we're going to look at this method in detail. We call a rational fraction a function that can be written as a polynomial on the top, which I'm going to call n of s for the numerator, and a polynomial in the bottom for the denominator. Everything is in terms of s because we're talking about Laplace transforms here. It is important to require that the polynomial on the top has a degree strictly smaller than the polynomial on the bottom. We're also going to discover irreducible quadratic forms in our partial fraction decompositions. So let's give it a definition. We call a quadratic form s squared plus 2 alpha s plus beta squared an irreducible quadratic form if alpha squared is strictly smaller than beta squared. In this case, this polynomial will not have real solutions, and therefore breaking into the product of two smaller linear terms will not be possible unless we use complex numbers. When doing partial fraction decomposition, we always start with factoring out the denominator. And any polynomial can be factored out in a product of linear factors of the form s minus alpha. Sometimes those factors may be repeated several times, and irreducible quadratic factors of the form s squared plus 2 alpha s plus beta squared. And when factoring out the denominator, we always find ourselves in one of those four cases. We may have a simple root, and therefore the factor s minus alpha repeated only once, and therefore the fraction looks like whatever it was on the top, and the denominator has only one term, s minus alpha, on the bottom, and the partial fraction of it will contain only one term with s minus alpha, and perhaps other fractions. Another case is the factor s minus alpha repeated n times. In other words, we start with a fraction that has, among other factors, s minus alpha repeated n times. Then the partial fraction decomposition will have n fractions with s minus alpha on the bottom. but each other fraction will have a higher power of s minus alpha. And perhaps we may have other fractions. Another case is when we have a single irreducible quadratic factor. In other words, we'll find a factor that we can't break into two linear factors. In the decomposition of the denominator. And this will lead to the following fraction. In the partial fraction decomposition. Apologize, this has to be plus. In the fourth case is when we have repeated irreducible quadratic factor several times. As you may already have guessed, this leads to several fractions which all start with power 1 on the bottom and go all the way to power n. The advantage of partial fraction decomposition is that it gives us fractions for which we can find the inverse Laplace transforms in the table. The hardest case is the fourth case, and we'll take a look at this a little bit later. But all the other cases are quite easy to deal with. So first, let's look at what kind of partial fraction decompositions we can get for different fractions. For the first example, here we can see that I can factor out s cubed from the denominator. And what's left is s squared plus 4s plus 3. The top stays the same. We can further factor out the denominator. Into s cubed times s plus 3 times s plus 1. Therefore, the partial fraction decomposition is going to have 5 fractions. 3 for s cubed, 1 for s plus 3, 1 for s plus 1. S cubed is going to generate fractions with s, s squared, and s cubed in the bottom. S plus 3 and s plus 1 will have only one fraction for each. And finding inverse Laplace transforms of these little fractions is quite easy. A over s is going to have a heaviside function, b over s squared is going to have a function t, and c over s cubed is going to have a function t squared. S plus 3 and s plus 1 will both generate a corresponding exponential function. First is going to be e to the minus 3t, and the other one is going to be e to the negative t. The next fraction keeps the numerator, but the denominator is changed. Now we have an irreducible quadratic factor here, and another irreducible quadratic factor here. Therefore, we're going to have two fractions of the third kind. We're going to have one fraction with just s squared plus 1 in the denominator, and then another fraction with s squared plus 4s plus 5. The first fraction quite easily can be broken into bs over s squared plus 1 and d over s squared plus 1. And the first fraction is going to give us cosine, and the next one is going to give us sine. In order to see better what's going on with the second fraction, what kind of function this will generate, let's break that even further. So this is going to be cosine. This is going to give us sine. I'm going to complete the squares on the bottom. Now that's s plus 2 squared plus 1. So we'll have to write it as a series of shifts, because we can see the denominator shifted, but the numerator is not. So we'll have to write it as shifted fractions. So I'm going to copy the first two fractions. And I'm going to use the magic of mathematics to break the last fraction into something with s plus 2 in the top. And then if you notice, I added two copies of e that weren't there before. So I have to subtract them out. Now we can see that the first fraction is just a shifted copy of the cosine transform, and the other is a shifted copy of the sine transform. Alright, let's look at another example. For this one, we can notice that the denominator can be factored as s squared minus 4 times s squared plus 4. And s squared minus 4 can be factored even further. And s squared plus 4 is an irreducible quadratic factor. So the partial fraction decomposition is going to have a single fraction for s minus 2, a single fraction for s plus 2, and a fraction for a reducible quadratic factor s squared plus 4. The last example looks horrible until you notice that the denominator is simply s to the fourth minus 4 squared. And factoring it out gives us s squared minus 2 times s squared plus 2, the whole thing squared. Going further, we have two repeated factors. Two repeated linear factors s plus square root of 2, and two repeated factors s squared plus 2 squared. The partial fraction decomposition is going to be quite long. It's going to be a over s minus square root of 2 plus another fraction with s minus square root of 2. This time it's going to be squared. Two fractions for s plus square root of 2. And also two fractions for s squared plus 2. I want to point out that for each one of those cases, the number of unknown variables corresponds to the power in the denominator. So here we have 8 unknown variables and the power in the denominator is 8. In this example we have 4 unknown variables and the power in the denominator is 4. Here again we have 4 unknown variables and the power in the denominator is s squared times s squared, so it's 4. Here we have 5 unknown variables and the power in the denominator is 5. This is always going to be the case. So when you're doing partial fraction decomposition, it's a quick way to check if you're doing everything correctly, just to see how many unknown variables you have and see if that matches the degree in the denominator. What I want to do now is to look at a couple of examples where I'm going to be looking for the Laplace transforms, and this way we can see how each one of those types of partial fractions transforms into inverse Laplace transform. The partial fraction decomposition for this one must involve the terms with s minus 1 and s plus 1. So this must be two simple fractions. I have pre-computed the coefficients, and I know that a equals 2 and b equals 1. Therefore I have fractions 2 over s minus 1 plus 1 over s plus 1. Therefore the inverse Laplace transform of 3s plus 1 over s squared minus 1 has to be the inverse Laplace transform of 2 over s minus 1 plus the inverse Laplace transform of 1 over s plus 1. And we know that these Laplace transforms correspond to exponential functions. The first one is simply 2 e to the t, because alpha is going to be 1 right here. And the next one is simply e to the negative t. So the simple partial fractions with simple linear terms in the bottom are quite easy to convert into exponential functions. The next example looks quite complicated. We have power 6 in the denominator and we're going to have 6 unknown constants in this partial fraction decomposition. We can write the denominator as s minus 1 cubed times s plus 1 cubed which means that we're going to have three fractions for s minus 1 and three fractions for s plus 1. Again, I pre-computed the coefficients. A is 3, B is negative 4, and C is 4. D is negative 3, E is negative 2, and F is 0. So the inverse Laplace transform is going to be simply 3e to the t. I have to be a little bit careful with the other terms. So I do have minus, I will have some coefficient, and I know it's a shifted version, so it's going to have e to the t in it. If we cancel out the shift, it becomes 4 over s squared. And 4 over s squared is the Laplace transform of 4t. So I'm going to have a coefficient 4 and have a t here. The next one is also going to have e to the t in it because we have a shift s minus 1 in the bottom. 4 over s cubed has an inverse Laplace transform 2t squared. So therefore this is going to be 2e to the t times t squared. Now with the s plus 1, everything's going to be multiplied by e to the minus t. And the first term is simply just minus 3e to the minus t. The second term is going to be minus 2 e to the minus t times t. And the third term is just 0. And therefore when we have fractions of this form with linear terms to some power, we first get out the shift, we get out the exponential term, and then we'll look at the table and see what kind of a polynomial function t to what power is going to have this as a Laplace transform. And we also have to be vigilant to not forget about the n factorial term that's on the top. The next type of partial fraction is the irreducible quadratic form partial fraction. So the first thing you need to do is you need to complete the squares. Here it's going to be s minus 2 plus 9. S minus 2 squared plus 9. We can easily see that this is a shifted version of the fractions 1 over s squared plus 9. Thus the inverse Laplace transform of 1 over s minus 2 squared plus 9 can be written as e to the 2t of the inverse Laplace transform of 1 over s squared plus 9. What is missing here is 3 on the top, and I'm gonna rewrite it as 1/3 outside and 3 inside the inverse Laplace transform. And we know that this kind of Laplace transform comes from a function sine. So this is going to be 1/3 e to the 2t times sine of 3t. The last case is the one that's most complicated. Here again, first let's take out the shift. To do that, first let's factor out the shift. To do that, we first have to complete the squares. When I complete the squares, I get s minus 1 squared plus 4, and the whole thing is squared. Therefore, the inverse Laplace transform of 16 over s minus 1 squared plus 4 squared must be the same as e to the t times the inverse Laplace transform of 16 over s squared plus 4, and the whole thing is squared. What we have to do now is we have to construct the term inside the inverse Laplace transform as a derivative of terms that correspond to the Laplace transform of sines and cosines. So let's find a derivative of the Laplace transform of cosine. And that's just 1 over s squared plus 4 minus 2s squared over s squared plus 4 squared. And if I simplify, this becomes s squared plus 4 minus 2s squared over s squared plus 4 squared. So that is 4 minus s squared over s squared plus 4 squared. This doesn't match the expression we have above, so let's try the derivative of a term that corresponds to sine. The derivative of that is minus 4s over s squared plus 4 squared. That doesn't match either. So the term we have up there is a combination of several terms. It's a combination of terms that the derivatives are in cosines, and possibly sines and cosines themselves. So what we have to figure out is how can we reconstruct (16 over s squared plus 4 squared) as a linear combination of a times 4 minus s squared plus b times negative 4s plus c times s over s squared plus 4 plus d times 2 over s squared plus 4. This looks like an overkill, but it really isn't. And the solutions are positive 2, zero for b, 0 for c, and 1 for d. If you try to simplify it, you're going to get 8 minus 2s squared over s squared plus 4 squared plus 2s squared plus 8 divided by s squared plus 4 squared, and you can easily see that this does simplify into 16 over s squared plus 4 squared. Therefore, the inverse Laplace transform of 16 over s squared plus 4 squared becomes the inverse Laplace transform of 2 derivatives of a Laplace transform of cosine plus 1 inverse Laplace transform of 2 over s squared plus 4, which corresponds to sine. Well, when we take a derivative, that means we're multiplying by negative t. So this is going to be minus t minus 2t times cosine of 2t plus single sine of 2t. And that's not it, because the final answer is the original function was shifted, and so we have to multiply everything by e to the t. And if you did enjoy this example, I can understand you. I did this example only to show that dealing with functions like this is somewhat complicated. The last problem that I want to consider today is an initial value problem with a somewhat complicated right hand side. Just as before, we're going to compute the Laplace transform of the left hand side. And that is s squared capital Y of s minus s times y of 0, which is 3, minus y prime of 0, which is 1, minus 2 multiplied by s y of s minus y of 0 plus the Laplace transform of y. If you simplify, y of s gets coefficients s squared minus 2s plus 1, get minus 3s plus 1. The Laplace transform of e to the minus t plus sine t plus t equals 1 over s plus 1 plus 1 over s squared plus 1, and t has a Laplace transform 1 over s squared. Therefore, if we set these things equal to each other, we get that y of s times s squared minus 2s plus 1 minus 3s plus 1 equals the Laplace transform of the right hand side. We move the 3s plus 1 minus 3s plus 1 to the right, and then divide by s squared minus 2s plus 1, and we get the following. S squared minus 2s plus 1 can be written as s minus 1 squared. And so all that needs to be done right now is to find the partial fraction decomposition for these fractions, and then use tables to invert the Laplace transforms. And you can clearly see what kind of partial fractions we're going to get. We can get something with s plus 1. We're going to get something with s minus 1. We're going to get s minus 1 squared. We're also probably going to get a fraction for the irreducible quadratic. And we're also going to get two fractions for s squared. This is quite a lot of work to figure out these coefficients, and I would rather do them with Mathematica. This example does show you how you can use partial fraction decomposition to invert the Laplace transform that you get out of this initial value problem. I think this is a good time for us to switch to Mathematica and recompute the solutions to the problems we just looked at. The first was the partial fraction decomposition. And we had the following fraction. If you compute partial fractions, we get the term with s cubed on the bottom, s squared on the bottom, s on the bottom, 1 plus s, and 3 plus s. So I'll skip part 2, 3, and 4 of the example 1 and compute the inverse Laplace transforms and partial fraction decompositions that we did for example 2. The first one was partial fraction decomposition of 3s plus 1 divided by s squared minus 1. And the coefficients are 2 and 1. And if I do inverse Laplace transform of this fraction, then we get e to the minus t and 2e to the t. That's exactly the answer we got in our notes. The other examples are no different. We had 16s plus 16 divided by s squared minus 1, and the whole thing was cubed. And we had only 5 fractions out of 6 because one of them had coefficient 0. And if we do inverse Laplace transform of this fraction, then we get exactly the terms we expect to get. 3e to the t for the term here. We get minus 3e to the minus t for the term here. We get negative 2 e to the minus t. We should get negative 4 e to the t times t. And we should get positive 2 e to the t times t squared. The parts 3 and 4 were already in the partial fraction decomposition form, so all I want to do is to find the inverse Laplace transform of each one of those terms. And Mathematica gives us the answer involving complex numbers. We can use the function full simplify to express it in the terms that are more familiar to us. and we get e to the 2t, that was the shift, we get sine of 3t, and we get the coefficient 1/3. And if we try to compute the inverse Laplace transform of the most complicated term we had, then again, after we use the function full simplify, we get the answer we got before. The last thing that we did was solving the initial value problem. And we had y double prime minus 2 y prime plus y. That was equal to e to the minus t plus sine t plus t. Just as before, I'm going to switch all the Laplace transforms. The function y of s, I know that y of 0 is 3, and y prime of 0 was 1. And let's solve for y of s. So what we need now is we need the inverse Laplace transform. But before we check if this is the right answer, I want to look what is a partial fraction decomposition of this big fraction. And let's see if the terms here can be easily identified. 2 over s is 2 times the Heaviside function, and it corresponds to the term 2 that we have in the solution. 1 over s squared should correspond to the term t, and we have it here. S minus 1 should correspond to the e to the t, and since we have a coefficient 1/4, we also have a coefficient 1/4 over here. S plus 1 with a coefficient 1/4 translates into e to the minus t. And the last term is 1/2 of the Laplace transform of cosine, and we have exactly that in our solution. So how do we check if this is a correct solution? Well, what I'm going to do is I'm going to define a new function. I'm going to call it ys for y solution of t to be exactly that. So this defines a new function, and what I'm going to do now is I'm going to check if ys of 0 is 3, and it is. What about y prime of s at 0? Ys prime at 0, that's 1. What about plugging it into the equation? Well, the original equation was this. So what I'm going to do is going to keep a copy over here and then just reevaluate everything with ys and see if it does equal to terms we have. And it doesn't look like it, but if we simplify, I'm sure that simplifies into what we expect it to be. And that's exactly e to the minus t. There's t and there's a sine of t. So this means that this function is indeed a solution. And that's how you can check whether or not the solution you produced satisfies the differential equation. Alright, I hope you enjoyed it today. This is where we're going to end, and I'll see you in the next video.